Right, good afternoon. Today's little talk is about Matlab Simulink and in particular the control system toolbox. Now, the control system toolbox is a sophisticated part of software within Matlab that allows you to design flight control systems. And this control system toolbox is used by all of the major aerospace flight control system players like BAE Systems, Airbus, and a whole range of other American and French and German companies. And the idea behind learning this toolbox is that as we go through the course, every single part of the course we can actually do using the control systems toolbox. So what it will allow you to do is, as well as developing your understanding of the course academically and from a mathematical point of view, you can also double up on your knowledge by doing it from a computer point of view, getting the same answers and then seeing the best and trade-offs between doing it through analytical methods and using computer systems. The bulk of your design work in industry will be using computer systems because they're more reliable and can do large complex systems very efficiently. So when we come to look at the course itself now, the first thing we're going to do is have a look at getting started with Matlab, and I'm going to look at some elementary data structures for you, vectors, matrices and arrays, and some of the built-in functions in Matlab and the type of processing it can do. It is a computer language at the end of the day, but we won't be delving too much into the computer language at the start, just using built-in functions to do the bulk of the computer work. We look at things called M files, which is a way of storing your information, storing your programs. We'll look at scripts as well, which is how to develop your M files. And then there's a secondary part to Matlab called Simulink, and this gives itself away. It's a simulation package, a very effective and powerful simulation package, easy to use, and we'll be looking at how to use that as well. So that's going to be the first part of the course. It's just a sort of overview of MATLAB Simulink from a general perspective. In the second part of the course, we're going to go through then these various topics. So we'll begin looking at block diagrams, which is again from a control system toolbox point of view. Something called transfer functions, which is the main technique for analysing and designing flight control systems. Then first order systems and second order systems. We'll also be looking at stability, PID control, state space and root loci. So there'll be a separate talk on each of these for you to work through. Now this also mirrors exactly what we're doing in the course, in exactly the order we're doing it in the course, and these first four go together to form the first exam question. Stability and PID goes together to form the second exam question, state space is the third exam question, and root loci is my fourth exam question. So also, as well as giving you a lot of knowledge about how to use Matlab and Simulink, it also allows you to understand the course, work through the course in a sequenced way, and develop your knowledge so that you can do those four exam questions at the end of the year. Now these individual learning materials are broken down into each one of these has a learning objectives, then a lecture, and then a video of me using Matlab to do some of those tasks. And finally, there's a knowledge check, which you can have a go at, which is where you then use that knowledge, see what learning objectives are, and see if you can then work through some little worked examples here to reinforce that particular topic. So that's the underlying structure now for our course. We're going to do Matlab and Simulink getting started. We're then going to go through these one at a time. So each of these has its own individual video and PowerPoint presentation. Each of these is broken down into a set of learning objectives and a knowledge check, which will check out that you've got all those learning objectives, that you've understood them and you can do them yourself in Matlab and Simulink. So that's the idea behind the course. I hope you enjoy it. If you do work through it all, by the time you finish this course, you'll have got a good grip on programming in Matlab and Simulink, and for your third and possibly fourth years, you can then use this knowledge effectively to push forward on things like find new projects and cut more coursework in flight systems and flight dynamics and control. So, and the final thing I like to say is that quite a lot of students have worked hard in this area, and when they've gone for job interviews, they've managed to get jobs working in flight controls for like the major players like BAE Systems and Rolls-Royce and Airbus. So there's a good opportunity here for you to not only learn about flight control, to learn about Matlab and Simulink, develop your skills and put yourself in a good employment position if you're looking for a job in flight controls in the future. So I hope you enjoy the course, and we'll now go on to some details about getting started. So welcome to this Matlab Simulink Control Systems Toolbox overview. The idea behind this is just to give you an overview of the course and what to expect and what you might expect to learn if you get involved in it. So we're really looking at Matlab and its Control System Toolbox, and this is a course overview, and I'm Dr. Tony Jones. So the aim of the course is to teach you how to use Matlab and Simulink to design flight control systems, and the way it's been designed is that it completely mirrors what you're doing in your lectures. So as you're going through your lecture material, if you do the corresponding part of the course in Matlab, it will help you to further understand what you're doing and develop computer skills as well as analytical skills. I've broken it down into small sections which mirror the lecture programme and give you an opportunity to expand your understanding through some computer exercises. Now, the main issues that we're going to look at are the thinking behind Matlab. Matlab is a sophisticated computing language allows you just about to compute anything you could possibly think of, but you can also use it in a much simpler way. So when we start off using Matlab, it's not going to be as a sophisticated computer language, more using Matlab data structures and functions to analyze flight control systems. As you become more familiar with the data structures and functions, you can then eventually glue those together and use Matlab coding as well to do more sophisticated things. But that's not for the moment. And the main package we're going to be using is the Control System Toolbox. This is universally used by all flight control people around the world to design flight control systems. Associated with Matlab is another package called Simulink, which is a simulation package. So we'll be looking at that, and the idea is we'll be then applying this technology to the design of flight control systems. Now, the structure of the learning materials is as follows. The presentations have been broken down so into the following sort of format. There's a set of learning objectives at the start, a technical presentation and some Matlab code examples. There's then a Matlab skills demo where I will work through Matlab real time to show you how to do different things. And then when you've looked at all that, you can then have a go yourself at doing something through a little tutorial example in the knowledge check. So the learning objectives of this particular little part is it's an introduction. So it's to give you an appreciation of the concepts behind Matlab and Simulink as a tool for designing flight control systems, and also highlight the main topics that we're going to address in the course and the structure of the learning. So it's important that you understand the structure of the learning, I think, in this particular online material. So we're going to start off looking at Matlab and Simulink from a high level point of view, an introduction, getting started,
data structures, built-in functions, M-file scripts and functions. And all that's part of a Simulink package. And the idea is that you can just appreciate how to use basic MATLAB competently. Then associated with it is with MATLAB is Simulink. So we then look at how to build up models in Simulink and use those models. Again, from an elementary basic point of view that you need to know to do all the different things. Then we can move on to the control system toolbox for flight control, and this has some specific areas to address now. So we've got block diagram reduction, first order systems, second order systems, stability, PID control, state space and root loci. And these form now the sequence of lectures that we can have in the course, and so they mirror on a one-to-one basis the lectures that we have and the learning materials. So for you an opportunity as you're going along to not only learn it from a academic and analytical point of view, but also from a computer point of view. If we look at the design process for flight control systems, the first thing we would do would be to get hold of some design specifications. Then we would draw up some functional block diagrams to sort of sketch out some block diagrams. And we transform this block diagram into a more physical reality, and then use that then to obtain block diagrams, signal flow graphs or state space representations. Then as we get multiple blocks, we use something called block diagram reduction to simplify our control system, and then we could use some analysis tools in MATLAB to actually do the design. So this is the whole process really, and we jump in mostly in steps 4, 5 and 6. Now MATLAB has a number of different things it can do, and the control is broken down into three main sections: what we call linear control, non-linear control and system identification. And if we look at what we're going to be doing is we're going to be mostly focusing on linear control in this part of the course using the control system toolbox and Simulink, but we can also have a little look at system identification as well. This is the process of how to work out what things called transfer functions are from physical reality. The other section, non-linear control, which is looks like things like sliding mode control and fuzzy control. They're also within the MATLAB toolbox, but we won't be looking at those at the moment. So let's look at MATLAB for control. The main idea behind using MATLAB is that we can build up block diagrams of flight control systems. So these are typical block diagrams of flight control systems, and these things inside here are called transfer functions. There's some controllers in there, and we have a feedback configuration. And the idea is that we can then go ahead and analyze these, and there are all sorts of tools now for feedback control system design within MATLAB to assess and look at the performance of these control systems we set up. So that's the underlying thinking of what we're doing. And as I say, the introduction to the control system toolbox will involve block diagram reduction, first order systems, second order systems, stability, PID control, state space and root loci. And if we look at those, and we look at those from using MATLAB to analyze them, and also Simulink. So we look at these from both perspectives and use the MATLAB features to better understand really what's going on in each of these topics. The first thing, I suppose, with the control system toolbox is we'll be looking at how to obtain so-called transfer functions. The transfer functions are the main design tool in flight control. And so you can go from, these are like differential equations, and we can transform differential equations into transfer functions. Each of these things we'll be looking at in some detail. Remember, this is an overview lecture at the start, so we're not going to go into detail, just to give you an overview of what's going on. But the first thing we need to do is go from differential equations to transfer functions. Transfer functions themselves can then be written as sets of polynomials. The top line we tend to call the numerator, and the bottom line the denominator. So as a general like structure, I tend to call the top line N or num or numerator, and the bottom line D or denominator. So N for top, D for bottom, as a sort of way of going forward. And if we factorize those polynomials we had here, then we get a factors coming out here, and the top line are always called zeros and the bottom lines are called poles. So, and we have a gain as well, so we have three things associated with our model: a gain, some zeros and some poles. And again, we'll be looking at the effect of poles and zeros as we go through the course. So one of the first topics we can look at is block diagram reduction. So if you've got some complex block diagram here, you need to simplify it down to a single block to be able to analyze it, and so that can be done in Matlab, and you can simulate these type of block diagrams in Simulink. So the first little part of the toolbox will be to show you how to use the block diagram reduction and then how to simulate blocks in Simulink. And here's just a very sort of quick idea of what we might do. We'll generate some Matlab code which will go and explain exactly how this works. This Matlab code then represents this block diagram and the code necessary to simplify it. So that's the typical sort of thing we'll be doing in block diagram reduction. First order systems is a simple type of transfer function where we have a gain here and something called a time constant here, and we can go about analyzing. This is an elementary flight control element in a flight control system. We can go about analyzing those, and we can look at different versions of this. So we can use our block diagram reduction to simplify these blocks into this format here, and then we can pattern match to work out things like time constants and gains. And you can have some examples of this as we go through the thing. There'll be like tutorial examples where there'll be little worked examples for you to have a go at. And then we move on to second order systems. You can tell it's a second order system because we have an S squared here. In the first order system we just had an S, and again we can do things like block diagram reduction. We can do analysis on the second order system as well, and we can also do simulations of the any system using the Simulink, and we can look at the transient response at the output here. This is actually going unstable here, so the output's sort of coming along and then zooming off to infinity. So it's just showing that you can do all sorts of things within the Simulink environment to simulate the system you're looking at. We can then move on to look at stability testing, and the main stability test we can look at is the Hurwitz stability test. And what this indicates to us is if we have a feedback control system and some gain here, then at some value of gain, this control system is likely to go unstable, which means that if it was a real flight control system, then probably the plane would crash. So it's important that we know what values in these feedback control systems go unstable, and we can use the Hurwitz stability test and some software in Matlab to figure out when this occurs. And then once we've found out the value at which it occurs, we can remain on values lower than these numbers to retain stability. The next topic we'll look at is PID control. This stands for proportional, integral and derivative. So that's proportional, integral and derivative, and it's a special type of controller with a KP, a KI and a KD, so it's got three gains you can choose. And with the PID controller you can usually obtain high quality performance from a control system, and the job is to choose these three numbers correctly. If you choose the three numbers correctly, it works very well. Choose the three numbers badly and it could be very bad. Now Matlab has a number of PID controller functions, and we'll be looking at the design of a PID control system. You can tune it, you can choose these numbers yourself. It's called controller tuning, but Matlab also has a inbuilt tuning package which will choose the numbers for you to optimize the performance of the system. So you can see how to use these optimization tools to choose your best PID controllers. Another thing we'll be looking at is state space equations. This is where we can represent a transfer function in an alternative form, in a first order differential matrix form. this allows us just to have a slightly different perspective on control system design, and we can look at transforming transfer functions into state space equations and going back from state space equations to transfer functions. And so we'll be looking at feedback control systems with transfer functions in, developing state space equations for this, and then simulating the state space equations and showing that both systems behave in exactly the same way. That you can see you can switch between state space and transfer functions without even thinking too much. The final bit of the course is associated with root loci. This is a design technique invented in 1954 by a chap called Walter Evans, and it's one of the most popular design techniques in flight control, and it looks at closed loop stability and allows you to plot graphs of closed loop stability, and Matlab has some lovely tools for plotting out the graphs, assessing the performance, and also looking at the type of transient response you can get. And these are quite nice. You can go onto here, you can drag these points around, these little red lines, these little red dots, drag them around into different design locations, and then just switch, and you can look at the transient response you'd get at that particular location. So they're really nice tools within Matlab for analysing and designing and understanding how control systems work, and we'll be using these tools in the course. Some things we're looking at is conversion between different models. We've got transfer functions, state space, and pole zero form, and there's functions in Matlab that allow us to go any way in these, so you'll learn how to use all of those. So you can always transform your system into whatever format you fancy. Just to give you some idea of where you might be working up to, this is an altitude hold autopilot design, where we've got elevator and engine thrust coming into some flight dynamic equations here. The outputs from this system are things like pitch angle, pitch rate, vertical height, vertical rate, and we can then use those to design forward speed as well, and we can then use those to design flight control systems, which will say control the altitude of the aircraft and control its forward speed simultaneously, and allow us to assess how changing one thing affects the other one. Another example is that we can, a similar sort of example, this is the heading hold autopilot, where the outputs this time are roll angle, roll rate, yaw angle, yaw rate, and you can use this to design a heading hold control system which will control the yaw angle of the aircraft. And again, these are the type of things that we'll be analysing as we go through the course over the next couple of years. As a matter of interest, here's an example of the type of thing you can do in Matlab as well. This is drone control, where we have a drone control system here. This is a simulation of the drone, and this is part of the flight control system in the drone. And this is like this is a PID controller. This drone has 6 PID controllers which all need tuning, and you can then design the PID controllers. You can fly then the drone round in simulation space. But Matlab also has a facility where you can download this code here. This is like control code in Simulink. You can download the code into the real drone and fly the real drone. And so these are just some of the things that we can do within this sort of very rich Matlab environment. So just to have a quick recap then of what I'm talking about, you can watch some videos, you can work through some examples, you can then have a go yourself and practice and learn. You can look at transfer functions, block diagrams, first order systems, second order systems, stability, PID, state space, and root loci, as all have individual little sections on them. And the way that the thing is set out is there's a set of learning objectives for each one, technical presentation, some Matlab code, live demo of using Matlab, and then a knowledge check for you to have a go at. And just to give you something, this is a typical example. It has some learning objectives here which you can read through so you can see what you're going to learn. It'll then have some course presentation, be a PowerPoint and a video PowerPoint. then a MATLAB demonstration where I'll go through the code. I'll run it as a screen capture in real time so you can see how you can go from step to step and do the different things. And then when you've had a look at that, you can then go on to a knowledge check where there's something for you to have a go at to see if you can actually do what you should have learned in that particular module. So hope you find the course interesting. I've constructed it very carefully so as it fits in perfectly with what you do on the main part of the course. If you work hard at this part of the course, it will give you a deep understanding of the program itself. You'll become an expert at flight controls and put yourself in a good position to thoroughly understand the design of flight control systems in aircraft. Right, so this talk is on Matlab Simulink, and we'll be using Matlab and Simulink throughout the course. So it's a very useful package to master, and there's some help and support from me now for you to learn how to use it. So why Matlab in engineering? Well, it turns out that in engineering there's a lot of calculations to do, and we need a computer package that will do that. And over the years, Matlab has emerged as one of the main players in terms of engineering software that the industry uses, and certainly in the flight control area, aerospace engineers almost all use Matlab and Simulink. So Matlab and Simulink is a good package to know, and most aerospace companies will look for you to have some skill in that area. You can download Matlab for free from the Matlab site, which is MathWorks. If you use your university email, you'll be able to get a free version of it. And you can download the complete package. The only problem is it takes up an awful lot of memory in your computer. But it's a £50,000 package, and you can have it to use for the next 2 or 3 years, as long as you're at Salford. When you've loaded the package, there's this little icon will be displayed, and if you double click on that, then Matlab starts. Matlab itself, when it comes up, has a command as a window, and there's something called a command window, a current directory, and a command history, and also some area. It tells you what variables you've used in the workspace. It's got a number of features along here which allow you to load in, edit, and generally store and create programs. And I'll just show you how this command window works now. So here's the command window, and we've got things like new script. This allows you to make a new program. You can open a script, generate a new one. This is the Simulink tool here. If you click on that one, you'll get a Simulink environment to use. There are additional add-on programs that you can get in Matlab as well that do all sorts of things like drone control, car control, you name it. Neural networks, deep learning, you can get those through the add-ons button here. But for the moment, we're just going to use Matlab as a simple calculator. So if I put, say, A equals 12, it will respond with A equals 12. If I put B equals 6, it'll respond with B equals 6. If I put C equals A plus B, it'll know that 6 and 12 is 18. So we can use Matlab potentially as a simple calculator, but it also does complex numbers as well. So you could put, say, X equals 1 plus 3J, for instance. Now we've got a complex number, and we could put, say, Y equals 4 plus 5J, and then we could work out X times Y, simply by saying X times Y, and it'll then work out the corresponding complex number for us. So Matlab, not only can it do scalar numbers, but also complex numbers. When you type something into Matlab, it tends to repeat whatever you typed in. which can be a bit annoying. So if we put a semicolon after the whatever we've done, so put Q equals 9 and then a semicolon, the semicolon will stop it from repeating itself. So it now knows what Q is, because if we type in Q, we know what it is, but it stops it printing it back on the screen. So that's part of the Matlab environment. Let's just go on to the next slide. So this is where we can put in variables into Matlab, so we can give it a name, equal sign, and a number in there. If you want to have a comment on a line, you can use a percent at the front. Anything after the percent sign becomes a comment, and it ignores this stuff here, just ignores it. So that can be handy sometimes when you're writing a program. You might want to put the odd little comment in, so when you come back to use your program about a year later, you might have forgotten what it did. So if we put A in, we could put it as 12. A times 2 would give us 24. If we put B as 10, C as A plus B, we've seen this at work within the workspace. Next thing we've got is an operator, which means if you do, say, 1:10, it'll give you numbers 1 to 10. If you do 1 to 10, it'll give you numbers 1 to 10 with steps of 2 in, so it'll give you 1, 3, 5, 9, 7 and 9. So this can be handy sometimes for setting up structures within Matlab. If we just have a look at that, it's not very important, but we could put, say, 1:10. It's going to give us 10 numbers. We could put x equals, open brackets, 1:2:10. This is going to give us numbers from 1 to 10 with steps of 2 in. And in this particular case, we put them into an array as well, which is a handy structure. This is a little structure we've got in Matlab called an array, and we've got another structure called a matrix that we can use, and we'll be using the array quite a bit in our control course. So that's just a quick on that. We can also use the colon operator to run through numbers. So this will give us 3, and then it'll go 2 and 3 in this particular instance here. So it'll give you A, 3, and then it'll give you the second and the third elements as well. So this is what I used a moment ago to set up an array structure. Not very often in Matlab, but you might want to find out what a variable is. So if you put disp and then open brackets and what the variable is, close brackets, it'll print out whatever x was, which can be sometimes handy. If you want some sort of text inside your thing, if you put disp and a single quote, then whatever text you want to appear, another quote and a ground bracket, if you type that sort of line in, it'll print out this, it calls this a string, and it'll print out hello world for you. And another command, it has input, that can allow you to input numbers. You could put u equals input and then enter a number, and you could enter a number, assign it to u. So you could run that line, and you would say you typed in 2, it would make u equal to 2. There's also a command called fprintf, and fprintf /n gives you a new line. This then prints out the variable here. %f gives you a floating point number and some units here, so the number that you've typed out will come out here. Whatever r has to have a value, unfortunately, for this line to work. So that's a slightly more complicated line. Maybe we'll come back to that one at some later point. Here's a little program that we're not going to use at the moment. Now, one of the things you might want to do in Matlab is you can use it as a calculator, but you can also generate files as well. So when we're using Matlab, we're going to be generating files, that's program names, and writing stuff into there. The advantage of that is that you can save these, and then you can come back and reuse them. So this is using the script feature in Matlab. So if you have a look how to use the script feature, so we go into new script, and it would come up here, and then we could type something in here like, say, a equals 1, b equals 2, c equals 3, and d equals a plus b plus c. And then we could save this. So we could run this if we wanted to by clicking on the run button. So we click on run. It asks us to give it a file name now. So I'm going to call it prog1, and it'll save it, and then it'll run it. And so it's then whatever this is in here appears here as some calculations. So this is, we're going to make use of these files. You could then do save. You can do save as, if you want to call it something new, say prog2. So you could save it as prog2, and then later on you could go back to open, and then you could open prog1 or prog2 depending on what you wanted. So you've got the new, open and save to manage your files as you generate them, and you've got the run button up here to run whatever your script file is. This is the best way to handle a MATLAB program. So we have script files, so we've looked at those, and as I say, these script files, you can type in variables in here, and when you come to run the program, then save it, it will run it as whatever's in your script file. That's quite handy. And the next thing to look at is matrices and arrays. We might want to enter a matrix into MATLAB, and here's an example. So to put a matrix or any data structure into MATLAB, you've got to use the square brackets. Now if we just put commas in between them, it'll be classified as an array, but as soon as you put a semicolon somewhere, it classifies that as end of line. So this is going to be 1, 2, 3, then a new line, 7, 8, 9, so it's going to give us an array or matrix 2 by 3, with 1, 2, 3 in the first row, 7, 8, 9 in the second. If we didn't have this semicolon here, but a comma instead, so rub that out, then it'd just be an array with 1, 2, 3, 7, 8 and 9 in. So this is a good way now of getting structures into MATLAB. Let's have a quick look at that. So I'll just delete this, cut that. So I could put, say, A equals open square brackets 1, 2, 3, 4, 5, 6. Now, you don't need to put commas if you don't want to, but I'm lazy, so I don't. If we then come to run this now, then it defines A as 1, 2, 3, 4. Fortunately, it's got 5, 6 there, so it's got them all in, but you can't see them because of the nature of the screen. If we'd put, say, B equals open square brackets 1, 2, 3, then a semicolon 4, 5, 6, then what we've done now is, because the semicolon is put this as a first line, this is a second line, so it'll now form a matrix B. So if we run this one, now get a matrix B, which is 2 by 3. So this allows us to put in arrays and matrices in. And the other little trick we've got available to us, if we put C equals A and then use the dashed, the sort of apostrophe sign, this corresponds to transpose. So rather than this being a 1 by 1, 2, 3, 4, 5, 1 by 5, you can make into a 5 by 1, so into a essentially looking like a vector. So if we run this now, you can see that C comes out as a 1, 2, 3. It's got 6 elements in, but C comes out as a vector, whereas A comes out as an array and B comes out as a matrix. So using these simple structures now, we can enter things like matrices into and structures into MATLAB. Now, another property of MATLAB, which is handy, is that once you've defined some of these data structures, you can use them to represent polynomial structures. So this is, we're going to use this a lot. So say we've got a polynomial x cubed plus 4x squared plus 2x plus 9. We could represent that as an array, putting a equals open square brackets 1, 4, 2, 9. So what this is doing is we could use this to represent a polynomial now from x cubed, 4x squared 2x plus 9. And then we could do some operations on this. Now, there's loads of commands in MATLAB. You can learn MATLAB commands for the rest of your life. There's millions of them, but you just need to know the ones that are useful to you. So there's a command called roots, and what this one does is it works out the roots of a polynomial for you. So this would work out then the roots of that cubic equation. So if we run this, and here are the roots. It's got a real root at -4 and 2 complex roots. MATLAB uses I for the imaginary. Some people use J. So there's an example now of entering an array into MATLAB and working out some roots. So this is where we've come back to our example now. This semicolons are representing a new line, and so that's going to represent a matrix thing. Now we've got additional matrix operations. We've got addition, subtraction, multiplication to the power, so you can raise a matrix to a power. You can transpose it. So you've got all these quite useful commands now to manipulate matrices as well. We're probably not going to use these a great deal for the moment, but just know that they're there. So as an example, if we got A as a 2 by 2 and B as a 2 by 2, we could put C as A times B, and that will multiply A by B. If we put a dot in here, it multiplies an element at a time. So I'll multiply that by that, that by that, that by that, and that by that if you wanted an element operation. So the dot is included to represent like an element operation, whereas this times is the normal matrix operation. If we have a quick look at that maybe in MATLAB. So let's put a semicolon there, shall we? Rip this bit out here and put B on a new line. B equals, let's make it say 3, 4, semicolon 5, 9. And we could do C equals A times B. And we could put D equals A dot times B. So we're going to use a dot, not a comma. That will completely muck it up for us. There we go. So the first one will work out the matrix operation A times B, and the second one will work them out element at a time. So here's A, here's B, here's if we get multiply this by this, we'd get this. If we do the dot one, it's then 1 times 2 giving us 2, 4 times 4 giving us 16, 2 times 5 giving us 10, and 9 times 9 giving us 81. So that does the element by element one. This does the sort of complete matrix one. Next thing you can do is any element of a matrix you can represent by any variables you like, really, but 2 variables, let's say, in this case it's I and J. These are not the complex variables, these are just any old variables. We could call them N and M if you wanted. So if we made A equals zeros 2, 2, zeros is a command in MATLAB that gives us a matrix full of zeros, and it will give us a matrix of size 2 by 2 full of zeros. We could also do matrix tricks, like if we wanted to add element A11 to A12 to A22, we could use this type of structure to add elements up. So an element in a matrix can be accessed through A round brackets and then its index in the matrix. So these are extra little things that we might want to use when manipulating matrices, but we're not going to probably using these much in this first semester. The next little trick is the colon operator. So this one allows us to run an array between one value and another. So this is going to go from 3 with a step of -2 down to 11. And it will then assign x to that particular thing, and it will generate an array for us. This will be they call it a row vector, but I would call it an array. So let's try that one, shall we? We've got x equals 3 minus 2 to minus 11, see what we get. So if we go into Matlab, and we might as well do it here, so we put x equals open square brackets 3 colon minus 2 colon minus 11 even, and then so this is going to give us an array now starting at 3, stepping down every time minus 2, so it's going to be 3 1 then minus 1 all the way down to minus 11. Run this, then we get this thing here, and there's our little array there starts at 3 minus 1, then just keeps on going down by 2 every time till it gets to 11. I'm just going to close it off so we can see roughly what we're doing. So that allows us to generate arrays of certain styles and certain structures. This one would like to do elements 1 to 3 on the second column. So if you wanted to do a little bit of more finesse, you could use a little bit more detail in there. So Matlab allows you to do quite a bit with matrices. All zeros is the zeros command. Ones fills it up with ones to generate a matrix. Random would generate with random numbers. Matlab can generate random numbers between 0 and 1. So this would fill them up with random numbers. Size 3 by 5, but all the numbers inside there would be random numbers between 0 and 1. And another one is rand n, which will give you a more normally distributed set of random numbers. These are uniformly, and one is normally. Uniform normally means it's like follows a bell-shaped curve. So if we define a matrix, an array A, it would come out as that type of thing. If we put semicolons in here, it would come out as that way. And if we put a semicolon in there, the first bit comes in the first line, and the second bit comes in the second line. So we've looked at that, and that's how you can set up things like arrays, vectors, and matrices in Matlab. The main one we're going to be using is the array. The array is the one we're going to be using for generating structures like transfer functions and things like that. So this is a relatively simple one for us to start with to generate transfer functions. So here's just a little example here. There's x, and here's another x, and here's a transpose. So we've looked at those within the little Matlab that we've done so far. If we want to set up a vector, say 1 to 6, then I'd prefer little square brackets in there, but you could avoid it. X is now give you 1 to 6 with steps of 1, and if we multiply, say y is 10 times x, it'll multiply the whole thing by 10 for you. Another command that we have in Matlab is a plot command, which we can probably just about see here. If we plot two arrays against each other, we'll get a nice little graph, but they've got to be the same size. That means you've got the same number of elements there as the same number of elements there. Right, so this little talk is about getting started with Simulink, an introductory tutorial. And this is the structure of our learning materials. So we've got learning objectives, and the first one is to become familiar with the Simulink environment, then to build a Simulink model, to simulate a Simulink model, and then send the resulting transient response graph to Word. So the first thing we're going to do is start off Matlab, and then we can start off Simulink. Now when we started off Matlab, Simulink appears as a little button here on the top line of the toolbar of Matlab. So we double click on that then, and up will start Matlab. So if we have a look at this, if we double click now on the Simulink button, then up appears our different ones, and the one we're going to go for is create a model. So we can double click on create a model, and this can take a few seconds to start up. We get ourselves a bit of a workspace here. So here's our workspace, and this is the create model thing. So if we click on this icon, we will start up, generate ourselves this file in which we can build up a model. So when we've got our model, the main thing we use is this little library here. So then we're going to click on this library, and we can generate different parts of control systems in the library, and we can then drag and drop them into this workspace. The moment the workspace is untitled, because it's the first workspace. Second one you make would be untitled 1, untitled 2, untitled 3, but best to give them a name to save them. So we go back to Matlab. Here we are now in our little environment, and we double click now on the library browser, and up comes now these. Now we've got all sorts of things here we can use here down here, and the ones we tend to use are commonly used blocks, continuous, sinks and sources. Those are the 4 main ones that we're going to use. So it's the first 2, and sinks and sources down here. But if we look up down here, we've got continuous. This is the main one that we're going to use. So we could click on continuous, and this now gives us some elements that we might want in our block diagram. So this is our different icons. Here's our continuous icon that we just pressed on. So we double clicked on that one, and we've come up now with these extra icons. Some of these have got things like transfer functions, integrators, state space equations, PID controllers, a whole range of things in here that we can potentially use in our workspace down here. So the next thing we can do now is try and take now some things from the library and put them into the workspace, and we do that by putting our mouse on top of the one we want, pressing our left mouse down, and then dragging it into the workspace, and then lifting our finger, and it will magically appear in the workspace. Let's have a look at that. So if we have a little go at that, if we click on the workspace here, so then we'll get the right ones to press. So if we click on the workspace here, no, it's not working. Let's try again. Got that one. Click on libraries. Then we take this transfer function one. So click on there, drag that one across, and in a few seconds it appears there. So we're going to take, say, let's have 2 or 3 of these, shall we? 1, 2, and a third one there. So there's 3 little blocks, and now notice the signals go in this direction. Now sometimes we might want the signal to go in that direction. So this one, say, wanted to go in that direction. We'd go put our mouse on top of there, then do a right click, and you'll then have flip and rotate and flip block. So it's a right click, this one, and that will convert the direction on this to a different direction. So that's quite handy. So that's a trick we can play within our little block diagrams. If we now go back to our Simulink starter, no, it isn't. So we can now go on to our next thing. So now this is where we've taken a couple across, and next thing we might need is a summing junction. So summing junctions come from commonly used blocks. So if we go to commonly used blocks now in Matlab, again go back to here, go to commonly used blocks, and we've got something called a summing junction here. So again, put our mouse on top of it, and then it's a left click and drag across, and say put it there. For instance, I just move that over there somewhere. So there's our summing junction, and we're getting a bit closer to what we want. So let's have a look what we're doing next. So there's our summing junction. Next thing now, we'll need a scope, and then we'll need a step. So we're going to need these from two separate libraries. That's a scope from sinks and a step from sources. So if we go back to Matlab now and go now to sinks, it's down there, and pick up a scope. The scope allows us now to watch what's going on. So that's quite a nice one. And then if we go back to sources, one of the main types of input we have is a step, which is the bottom of sources, to get one of those, and drag that over there. Now we've got the building blocks of a little control system. So now if we take our mouse here and drag it towards here with a left click, with the left mouse button down, it'll join them up for us. So we can join that to there, join that to there, join that to there, join that to there. Then we can join this one to there, say, and we can join this one onto there. And now we've got the makings of a little flight control system. Now, one of the things in the feedback control system, this has to be plus and minus. So if I double click on this and change the sign to a minus, you have to have plus and minus in feedback control systems, otherwise it's not going to work. The runtime of a simulation is set up up here, so we could change that number. At the moment it's set to 10 seconds, which is probably okay for the system. Notice now what we've got in these blocks are just simple transfer functions, 1 over s plus 1. Now we can change these using a polynomial structure to enter things into here. So we'll be looking at this in more detail when we look at transfer functions in the next talk, but we'll just do, say, this one for the moment. So we double click on this, you can now put a polynomial structure in here. So if we put, say, 1, 2 in there, and in here we could put 1, 4, 9, then this will give us a transfer function. And to look at the transfer function, if we open it up like this, it's given us a transfer function of s plus 2 over s squared plus 4s plus 9. So if we double click on this again, so we can see now that the 1 and 2 is the 1 and 2 here, and the 1, 4, 9 is the 1, 4, 9 of the polynomials here. So we can set up any polynomials here just by putting a little row of numbers, which are the coefficients of the polynomials, and then clicking on OK to make it OK. So say we're going to put this as 10 and over s plus 10. We could delete that one and make the 1 into a 10, and then when we click OK, that's become 10 over s plus 10. So then that allows us to build up a little control system, like get the elements, then we can connect them up. And then we've got our scope. Next thing we could do now is if we click now on the run button here, we can then run the simulation. And then if we double click on the scope, we can see the results of our simulation. So we go back to here. So go up to my run button, click on the run button, and with a bit of luck, the simulation will run. Here we go. And then double click now on the scope. So we double click, left click on the scope. It comes up with the transient response, which it hasn't seemed to have done. We'll try running it again. Haven't quite run the simulation, that's at all. It comes up with that little, if you notice, if I run it again, when it's done the simulation, it comes up with that little noise to tell you it's run the simulation. My computer must be running a bit slow. If we then double click on this, here's the simulation now that we obtained from our little feedback control system. And this graph now we might want to put into a Word document. So if we go on to Tools or even onto Files and copy to clipboard, then this graph now has been copied to clipboard. If I go down and open up a Word. See if I can find my Word somewhere here. Here it is. Open up Word. Now go for a new document. And if I do a paste, then my graph has now appeared in the Word document. So you can see it's quite a nice graph and nicely drawn, nicely. And you can actually, if you click on it, you can change its size as well. You can have it as big or as small as you fancy. You can actually put labels on this. You can put a label what the graph's called. You can put an axis and an X and Y axis labels on it as well. There's extra things you can do with this, which is quite handy. Just close that down. Don't save. So there's our simulation. So we've got our simulation. There's a transient response. It's a little bit different because the system's different. Here's a copy to clipboard. There's this copy to file. This is just showing how we might go if you wanted to flip a block. So, but we've looked at how to flip a block already. So next thing we want to do now is to save our Simulink file. So if we go down to here, what's gone wrong now? Let's close that a minute. Right, so if we go, having got to here now, one of the last things to do is to do save. So if we click on save, and then we can give it a file name. So I can put it as, say, call it model 1. Now, one of the things about MATLAB file names is you can't use white spaces. You can't have model space 1. If you try that, it'll say get lost. You must have no white spaces here. And you mustn't start the number off with a number at the start either. So if you put 1 there, it won't like that either. So letters at the first and no white spaces. You can use underscore. So it could be, say, model underscore 1. And then you click on the save and you can say where you want to put it. So I can put it in, say, desktop and then into, say, MATLAB. And I could save it in there. The advantage of saving is that you've then got it to come back to in the future. Now, one thing that can go wrong in a flight control system or in simulations is you forget to do the plus and plus. So notice now, this is the simulation here. It's quite it's called stable. It goes from one value to another. It doesn't do anything too bad. If we'd made a mistake here and we'd got a plus and a plus here, which we shouldn't have, this control system now is what's called unstable. And if we run the simulation now, look, you can see should have gone unstable. Look at that, plus and plus. Okay, and run. Now it should have gone unstable, but it hasn't, which is a bit of a shame. Maybe the gain isn't big enough. Anyway, you don't have a plus and minus. I need to have a plus and minus in there for it to remain stable. That one didn't work very well for me. If we change the gain here to, say, 10, and then run it again, might show it. Here it's gone unstable, it's zoomed off. This is an indication of an unstable system. That's where your transient response zooms off to some quite big number here. Looks like it's about £10,000 or 10,000 numbers. If we change this back though to plus and minus, if we're lucky, it'll be stable. Which is now what we get. So this is like a stable response. It's got one value to another, quite stable along here. This is with the plus and minus here. But if we've got, in general, if we've got plus and plus here, it will go unstable. Right, so we just minimize that for a second. Minimize that one. And now there's something for you to have a little go at. So what I want you to do is build up this little simulation in MATLAB. Notice you're going to have to flip that block to put the 5 in there. and see if you can run this as a simulation and then stick your response into Word. And then you'll have then mastered building a model in Simulink, running a simulation and sending data into thing. And you have to double click on this box. I'm going to put a 2 and a 1 and a 0.5 into those boxes to get that numbers there. So there's your first little introduction to Simulink. It's a nice drag and drop user-friendly environment in which you can build up the most complicated and elaborate little control systems you can think of. So good luck with your little assignment there. Right, this is our block diagrams in Matlab and Simulink lesson, and what we're looking at in this particular video is how to enter transfer functions into Matlab, how to build them up into block diagrams, and how to do block diagram simplification so we can simplify a complex block into a single block. And we're going to be using Matlab and Simulink to do this. So let's look at the learning objectives. First thing we're going to do is how to enter a transfer function into Matlab. Then become familiar with block diagram simplification. Then use Matlab commands to actually simplify some block diagrams. Finally, simulate a complex block diagram, simplify it, and then compare the two, hopefully showing both are the same, therefore verifying it's correct. This is one of the things it's useful to do in Matlab. You can do things a couple of 2-3 ways, and all the answers should be the same. So then if you've done it correctly, they'll all be the same. The chance of doing it incorrectly and them being the same is quite small. So let's have a look. The first thing is, with our transfer function, we have a set of zeros on the top and a set of poles on the bottom. And these are represented by polynomials. And we can represent the polynomials in Matlab using square brackets and then put in the coefficients of the polynomials in descending order. So it's quite simple, just the b goes there, that one goes there, the last one goes there, this one here goes in there, this one here goes in there, and the last one goes in there. They go in square brackets. You need to give them a name, call them what you like. I like to use n or num, or say num1, num2, num3, den1, den2, den3. Once you've done that, you can use a special command in Matlab called tf. Tf stands for transfer function. And again, here you have a name, so you can call it what you like. I tend to call them sys1, sys2, sys3 to keep a consistent story going. And then whatever you've defined here, you put in there. And that allows you then to build up little transfer functions in Matlab. Now, if we're doing block diagram simplification, we need to know 3 main tools. One is to multiply 2 together, which we can use a series command, or the one I prefer is just a times. So if that's defined as G1, that's defined as G2. The new system could be G1 times G2. We've also got parallel, which when the blocks are in parallel, we can use the parallel command or just plus. This is the one I prefer, G1 plus G2, and that'll add those up, convert it into a single block. The very useful one here is called feedback, and in feedback you have to have G1, the one in the forward loop, first, and the one in the feedback loop second. And obviously G1 and G2 are defined as transfer functions within Matlab. So let's look at how we might do this now. So this could be some Matlab code now that could enter these 2 transfer functions into Matlab and multiply them together. So what I've done is I put n1 is 4, it's in square brackets, notice, and then the d1 is 1, 1. And I put sys1 is tf n1 d1. For this one, I've got a 6 in here on the top. I've got a 1 and a 2 in there. And then sys2 is tf n2 d2. If I want to multiply them together, I can just say sys3 is sys1 times sys2. So if we have I'll just copy this bit of code here, so we copy that code out of there and do a copy and then go into Matlab. Now this is Matlab now, so if we go into new script, Here we go, new script. This opens up new script. We can now paste that code in there. So there's the code. So it's N1 is 4, D1 is that's sys1, this is sys2. We can now run this code by clicking on the run button here. And we'll just save it as any old thing. No, it doesn't like this. And here we go now. So let's have a look what's happened. So it's put in now. It started off and it's put in N1 is 4, D1 is 1, 1, there's sys1, 4, 1. Then it's got N2, D2, there's sys2, and it's multiplied them together to give sys3, which is the answer here. And there's our little example. So that's our first little thing. So we go back now to our presentation. So that's our first little trick. We can enter transfer functions in, we can multiply them together. And so that's just showing now the code going in there, and this is what we got as the answers. You can have a go at this. Our next one we're going to do is this one here now. This has got a 4 over s plus 1, 6 over s plus 2, but it's in the feedback loop now this time. So we enter the 4 square brackets, the 1 and the 1, 1, 1. And then so there's a little bracket missing here, isn't there? So if I can do the correction here. No, it won't allow me to. Anyway, there's the TF, N1, D1. There should have been a round bracket there. Then we've got N2 as 6, D2 as, well, it probably is there, but this is hiding it. I'll move that a little bit. There we go. Right, so there's the, got an extra bracket now because we put it in. So there's a sys1, then N2 is given by top line 6, it's 1, 2, sys2, and then we've put sys3 is feedback sys1, sys2. So if I again take this bit of code here and copy that, and then go into Matlab and do a new script and do paste. There's the code. If I run it, I'm just going to give it some name because it prefers to have a name. And again, this is done a more complicated one now. Remember, this has done this for us. It's taken this complete feedback system here, and it's converted this now into a single transfer function, of which this is the answer here. So this is a handy, very eloquent tool really within Matlab for doing block diagram simplification. So there's the little example again. So here's a slightly more complicated one this time. We've got the system here. You can give them little names if you like as well, but when we're in Simulink, you could actually, the names you use here, you could use here. We'll show you that in a moment. So we got, say, the 4 and the 1, 1. So this is sys1 here. Then sys2 is the 6 and the s plus 2. And this one now, slightly odd because it's got an s on the bottom. So it's s plus 0. So that's why this is a 0 there. So that's a 1 and a 1, 0 because this is s plus 0. And then I've said on this one now, these two are in parallel. So I've said plus. So sys3 I get by taking, this isn't quite right now, is it? This should have been that's sys1, that's sys2, and this is sys3. So that should have been sys4 really. That should have been sys4 is sys3 plus sys1. So that's a slight improvement as we go along. And then, so that's simplified that down to sys4. And then we need to change this to a sys5. And then we need feedback on this one, which is sys4, with this one here, which is sys2. So there's the code now for this bit here. That one enters in this one enters in that, this one enters in that. Then we add these two together now because they're in plus and plus here, and they're in parallel. So we say that this is sys1 plus sys3. That gives us sys4. So this is now represented by sys4. That's in a feedback loop. So sys4 is the forward loop element, and sys2 now is the feedback element. So again, if we took this bit of code and copied it, we can go to MATLAB and get a new, click on new script, and then just do a paste in here. So there's the code now. Then go up to here. So to run the code, we click on the run button here. It'll ask us for a name for it, which is a bit of a nuisance. I'm just going to call it any old thing. And here's the final answer now. So you can see that as the transfer functions go along, they build up, and eventually we get our answer here. So that's how we could use MATLAB to do block diagram simplification. And there's a little example. I think this one had a mistake in it, so this code might not be 100% correct, but I've given you the right version now, so you can have a little check on that. So here's another example now, where we've got something similar, but I've put an extra element in here, which is sys4. So there's sys1, which is this one here. Here is sys2, which is this one here, still this one here. Then we've got sys3, which is that one there. And then we've got sys4 now, which is this one down here, which is this one. So the first thing we're going to do now is multiply these two together. So we'll say that sys5 is sys1 times sys4. And then sys6 now we get by doing a parallel activity. So it's going to be sys5, which is the answer to these two, in parallel with sys3. So it's going to be a plus there. Plus, remember, does in parallel. And then having got that one, then we can do a feedback on the new, all that part there has been put in as sys6. So that's the sys6 there, and then the feedback element is sys2. So there's the code now for simplifying that block diagram. So again, if we copy that code like that, and do a copy, and then go into MATLAB, have a new script, paste it in, and then run it, and then we get the answer. So this one's crashed, unfortunately. So it tells you if it crashes what line. So it's line 20, and the problem with this one now is little interesting. In PowerPoint, it tends to make the first letter a capital, so it's put an S, capital S in there. So it's case sensitive, this. So it has to be sys6 then with a little s, not a big S, because it's all with little s's, and PowerPoint had made the thing into a big S. So watch out for that. Case sensitive. Even I can make a mistake on this. So run it again, and this time it runs correctly. And here we have our more complicated transfer function for the system. So that's a reasonably complicated block diagram to simplify. So that would be the code there for doing it. Be able to look at those. Now, what we can also do is, having done one of these, we could go on to check whether we've done it correctly by using Simulink to simulate the system, but also simulate the simplified system and see if they're both the same. So to do this, we need to start off Simulink. So normally go along here, find the Simulink button there, click on it, and then Simulink will start. So let's have a look for that. So you go along here. So we go into Home, and then here's the Simulink button here. So if we double click on this button here, and then we can do create model. So this gives us some potential now for building up a little model, and let's see if we can choose now a model. So we've created the model here, and here's our workspace, and now we can use the library to build up some transfer function. Remember that what we're going to do is we're going to click on the library. These come up. We're going to use the continuous transfer function thing. So we're going to click on that button there. Then we're going to have some transfer functions here, which we can drag and drop into our workspace to build up our block diagram. And the one we're going to do is the first one here, which is 4 over s plus, first example, 6 over s plus 2. So we're going to have a go at doing that one now, and let's have a go at doing that. So here we go. Go back into here, so I'll get it correct. Right, so we go into libraries. Takes a few seconds, my computer's not that quick. Then click on continuous, I'll even double click on it, and then we've got the different things we want. So the one we want is the transfer function. I'm going to put my mouse over this, so I'm moving mouse on top of it, then do a left, hold your left button down, so hold left button down, and then drag it across into there. And by magic, after a few seconds it appears. Then we can put another one across, like that, say. Now we connect these two up. We want to watch what's going on, so if we go back to here, we can remember got some of the tricks we've got. So the main ones used are commonly used continuous sinks and sources. So I click on sinks, I can get a scope. Scope is the main way in Matlab to watch out what's going on. And we also need a source, which is a step. They should have put these in common use blocks, but they haven't. So we're not far off now, but we need now this to be a 4 over s plus 1. So we double click on this, and now we have a polynomial structure here. So the first one is the same structure as we had in Matlab, so it's going to be 4. And if I click on OK, it's got the 4 over s plus 1. If I now go to here, I can double click on this, and this time this has got to be 6. It has to have the square brackets around, otherwise it will go mad. And this has to be a 2. Like that. And then there's our system. We can now simulate this by clicking on the run button. It's going to run for 10 seconds. And then if we click on here, it should give us the transient response there. So there's a transient response. Now we know what the answer to this is. The answer to this is given by 24. Let's go back to see if we can find the answer. It's going to be 24 over s squared plus 3s plus 2. So we know what the answer to this is. Let's just go back to Matlab. See if I can find here. Here's 4 over s plus 1. Here's 6 over s plus 2. So the answer would be sys2, wouldn't it? So if I go down to, if I run this, one, and I want sys2. Type in sys2, it'll tell me what it is. That wasn't sys2, that was a mistake. Start again. Wait a minute. It was, that's sys1, that's sys2. So we need sys1 times sys2. So you can type in here sys1 times sys2, and there we get the 24 over s squared plus 3s plus 2. So we know now this is the answer. So if we go back to Matlab now, and so we do copy one of these, copy, and then do a paste, get an extra block, can connect that up to there. Now we've got the scope here with just one input, but if we right click on the scope now, and it's got a feature here for signals and ports, and then number of inputs there we can change to 2. So by going to signals and ports, number of input, change that to 2, an extra arrow comes up here, I can connect that up to there. So I've now got a scope that can look at 2 things. So if we ran this now, obviously this system is different to this one, so this is going to give us 2 separate graphs. So if we run this, have a look here. So now we've got the 2 systems, and they're not the same, and therefore we get a different output. So if we were saying now this actually is the same as this, we'd know we'd made a mistake. So it's obvious. But we know that the answer now here is 24 and here the answer, or the thing was 1, 3 and 2. So that was the, so if you can't, sometimes if this doesn't fit in it, but if you get the box, just make it a bit bigger, it'll put the right numbers in for you. So hopefully now this out, because these two are the same now, these two outputs will sit on top of each other and we'll know we've done it correct. And there we are, they're both sitting on top of each other now. So just to show you that they are on top of each other, if we made that into a 23, which is quite close but not quite right, then what will happen now is when we run it again, they are almost the same but not quite, because one's got a 23 in and one's got a 24 in. So that's how we could use now our MATLAB. When we've simplified a block diagram, we could have the original block diagram, and then we could also have the simplified block diagram fed by the same input and feeding onto the same scope at the end. And if both appear the same, then we know that we've done it correctly. So this is what we were doing here, and we're looking at the output there. So you can do the same sort of thing now with more complex block diagrams. So here's an example. This is one again we looked at. This was what the answer was. So it'd be possible now to build this block diagram up, have this block diagram as a single block, feed it into this, and this one would feed into there. And then we could sort of compare the two to see if they were the same. So that's what's going on here. So there's the solution to that. I then simplified it and got that, and got the same thing here. So in this particular case, I've got a 1 over s plus 1 and a 1 over s plus 1 in here, and I've simplified it down to this block here. If these weren't the same as I did before, then you'll get a different output here. So here's a couple of things for you to check out on. Here's a little block diagram, quite a simple one. Enter that as the transfer function, put this as the feedback in, just going to be a 5, and multiply the whole thing by 10. It's because you've got a 10 in there. So build this up, run it as a simulation, use your block diagram simplification to simplify this down to a single block, and then try and run it, the two blocks in parallel, to see if they're the same. And then here's a slightly more complicated one for you to do as well. Simplify this system down to a single block, and then see if you can convert that into, well, a single block, and then put the single block down here, feed the same input into it, put the output onto here, and see that the two systems are the same. So this should have given you some knowledge now about entering transfer functions into MATLAB using the series and parallel commands, which are just basically plus or add, and the feedback command as well to do block diagram simplification, and also putting those things into Simulink to build up simulations of block diagrams, but also using your block diagram simplification to verify that it's been done correctly. So those are quite handy little tools for you to have, and will be useful throughout your course, because most of the work is involved with block diagram manipulation and looking at the performance of the block diagram. Right, this little talk is on root loci plots in MATLAB and how they relate to transient response in Simulink. Now, what is a root loci? So remember, if we've got a closed loop control system, it's got a transfer function in here and a controller gain there. And we can represent the closed loop characteristic equation as the equation 1 plus kgs equals 0. Now we could rewrite that as the product of the poles plus k times the product of the zeros. And this is called then the closed loop characteristic equation. And this equation will have different roots for different values of the gain here. So if we imagine plotting the roots of this equation as k changes between 0 and infinity, that gives us this thing called the root locus plot. And the root loci plot gives us information about first order systems, second order systems, stability, all on the same graph. So it's quite a handy graph to do, and it's very easy to produce in Matlab. So let's have a look now. What are learning objectives? Understand what a root loci plot is, plot a root loci in Matlab, assess the root loci plot for stability, use root loci to choose a controller gain, and simulate a control system when you've chosen a gain from a root loci plot. These are going to be our learning objectives, and let's just go back to our fundamental little equation here. So we've got the closed loop system, got a controller gain K there. This is the closed loop stability equation, and if we pass this polynomial as den and this polynomial as num to this Matlab function R locus, it computes the roots of this equation as K varies from 0 to infinity, and that's why you get a trajectory of plots and this thing called the root loci plot. Remember, it only requires you to define the open loop transfer function, but it does plot out the closed loop characteristic equation. Sometimes people get a bit confused about that. So with root loci, you give it the open loop transfer function, but you get a plot of the closed loop characteristic equation. So it gives you a bit of added value. So let's have a look at how this works. So we could have a little block diagram like this, and it's got a transfer function 3s plus 9 over s cubed 10s squared 12s plus 15, and a controller gain in here, and we could find out now how the system performance varied as we changed the gain, and we could do that by defining this little bit of code here. So down the numerator 3, 9, denominator 1, 10, 12, 15, and then put sys1 says tf num den, then r locus sys1. So define the transfer function, then the command r locus with the name of the transfer function in there, and bingo, you'll get a root loci plot. Let's have a look at that. So if we do copy that, and we can stick this now. If we have a new script, can paste it in there and run it, and let's give it a name, and there's the transfer function. Just check it's okay, and here's a root loci plot. Now in this case it can't go unstable, but if we put our little mouse on the top of the plot and do a left click, it'll tell us what the gain of that point is and where the poles are, what the damping ratio is, and if you consider that to be a second order pole, it'll tell you what the natural frequency of the pole is and also what the damping ratio. So if we move it a little bit, so move it that way, we can reduce the damping ratio. If we move it down, we can increase. So we're looking, say, for 0.5 there. We could go down until it gets to 0.5. Does it get to 0.5? This one doesn't get to 0.5, unfortunately. It's a bit unlucky, but anyway, it gets to about 0.48, and then that will tell us the gain at that particular point. That would be the natural frequency, that would be the damping ratio, that would be the gain at the point. And so this is how we could generate now something called a root loci plot in Matlab. So this is just indicating that. So we can then, by moving along here with the mouse, we go all along here, we can see what the gain is in the control system. That number is the number there for this particular point on the root loci, for which you have a certain damping ratio and a certain natural frequency, omega n. So it's like a second order system poles here. These are first order system poles here, and it'll tell you for either of them really what the gain, damping ratio and frequency is. Now we know that in the overall domain that this is the stability boundary down here. If you're on the stability boundary, you get a marginally stable oscillatory response. If you're over here, you get a decaying response. Here, stable on this side. On this side, unstable. If it's on the real axis, it zooms off. If it's imaginary, it sort of zooms off, but in an oscillatory manner. So we've got an idea about how to interpret the root loci from our work on first order systems and second order systems. And we can use that then to better understand a more complex root loci. So here's a more complicated root loci now. So we've got 1, 2, 3, 4 poles and 1, 0. And we're going to enter this transfer function here in and then plot the root loci for this. So the first thing I'm going to do, this is a slightly different way now of entering in the transfer function. I'm entering in this polynomial, that one, and that one. So that's the first 4 here. And then the convolution command multiplies two polynomials together. So this multiplies C by D, which then multiplies it by B, which then multiplies it by A. So it's like a nested convolution. And this essentially multiplies that by that, by that, by that, and calls it den. The top line is given by 3 times 1 times 1 times s plus 3. So it's 3, and that's a 1 and a 3, because it's a 1 there and a 3 there. And then the system, we can define the open loop transfer function as tf num den, and then do root locus, our locus sys1. I can also control the axes here. It's round brackets, then square brackets, x min, x max, y min, y max. If you need to control how much of the root loci you can see. So if we take this bit of code here now and copy that, we can use that then in Matlab to plot a root loci of that system. So let's get rid of that and do a paste. So there's our code. We now run it. There's our open loop transfer function, and here now is our root loci plot. So if we're over here somewhere, say down there, we know this is a damping ratio of 0.8, natural frequency of 3. As we move along here, the damping ratio goes down. So I can get to say 0.5 or something. Let's go for 0.5. There we go, damping to 0.5. The gain at that point is 79.7. Natural frequency is 5.12. So if we wanted to have the complex roots to have a damping ratio of 0.5, omega n of 5.12, we could choose a gain of 79.7. If we go somewhere more around here, we can find out this is where it goes unstable. We can find out where it goes unstable here. So if we click on there, that gives us a gain of 527. So at 527, it's just about stable, and it's just gone unstable, isn't it? It's 0.05. So I pulled it, dragged it a little bit back. I don't know if I can drag it that much. Not really going to drag in these. That's almost 0 now. That 513. 004 is quite small, still unstable. That tells us the gain now, which it goes unstable. This tells us the gain at which we can get a certain damping ratio out of the closed loop system. So again, the root loci plot can be very handy for that, and that's what we can do here. We can look for these points, we can look for points down there. We can use root loci plot to do that. So this has given us the gain where it goes unstable. It's hard to find the exact point because moving the mouse in that sort of small region is quite tricky, but it tells you what it's going to be stable or unstable. This number is not going to be far off, just 1 or 2 numbers off, but quite good. If we put that gain into a simulation, it would be marginally stable. So what we could do now is we could have a go at building this up now in Simulink and relating our root loci plot to a Simulink simulation. So I've got 3 over s plus 1, s plus 3 over s plus 4, 1 over s plus 6, and 1 over s plus 10. So that's my elements and transfer function. So if we go now into Matlab, and we'll go onto home and get Simulink going. I'll start with a blank model, and we're off now building this little transfer function. So we've got 4 boxes, so we're going to need 4 of these. That's 1, 2, 3, 4. So there's our 4 boxes for the elements of the transfer function. See if I can line them up. Then we'll also need now a commonly used block will need a semi junction, so I'll get one of those in. We'll also need to control the gain, so I'll get one of those in as well. So that's, we now need to go on to sinks, and we'll need a scope, and then go on to sources, and yes, you guessed it, we need a step. So there's our building blocks now for our little block diagram. To check out our, did something a bit odd there, let's cut it out. So connect down up to there, connect that to there, 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 and go down to here and zoom up there. So getting somewhere now. This has to be plus and minus, so click on that one, make that a minus, and these a few times now. First transfer function now is going to be 3 over s plus 1, so double click on that, and we can make this into a 3. That one's done. Next one we need s plus 3 over s plus 4. So MATLAB allows you to have the same number of poles and zeros, so we're going to have 1 3 over 1 4. So that's going to be that one. And then we need a 1 over s plus 6. So we can go onto this one and we can change that to a 6 like that. And then last one is a 1 over s plus 10. So I'm just going to change the 1 to a 10 by moving around a bit like that. And there we have our transfer function now. And let's see what we could check out now. Well, we know that going back to our previous little thing here, we got again about 520 here. This should be almost marginally stable from our root loci plot. So if we go back to here now and put in here 520, and then okay, run this as a simulation now. Let's just probably be okay over 10 seconds. Probably not long enough. And you can see now it's looking pretty sort of unstable-ish, isn't it? It's slowly growing, actually a bit bigger. So probably 520 isn't so good. So we could go down to maybe 510. See what that one does. I could run that one and see what's going on there. This is more looking like marginally stable now, isn't it? So if we go below 510, say we went to 500, then should be stable now, really. Yeah, this is sort of stable, slowly decaying, so it's showing it's stable. So here we've got our marginally stable case. If we chose a number bigger than 510, it's got 520. It's clearly going to go unstable, so let's just have a quick look at that. So say we did put in here 550 and ran it, and now it's clearly getting unstable, so we've got an unstable response there. And if we did choose, let's say we went for a damping ratio of 0.5, gain of 79.5, so we could, and we did that one a second ago, so we can go back to our root loci plot, interrogate it, go for a damping. Damping between about 0.5 and 0.6 is usually quite good in flight control systems. So if we go back to here, and we said when it's 0.5, it was about, that's close enough to 80, isn't it? So we'll call it 80, shall we? So if we go back to our root loci, choose 80 in here now, 80, and then run it again, then we get sort of a relatively okay response rate, don't we? It's doing about 10% overshoot. It's very quick, not too bouncy. So we can see that damping of 0.5 is giving us a relatively acceptable type of transient response for a flight control system. And that is a typical sort of what you'd call an okay response for if your flight control system was behaving like that. You certainly think in terms of damping, it was performing adequately. So that's how we can use our root loci plot now, by moving along here to choose gains and then stick those gains into the simulation and get some transient response, which is acceptable again. Now there's another thing we can do. MATLAB has a little thing called RL tool, which you have to pass the numerator and denominator to don't pass the transfer function to, unfortunately, you have to pass the numerator and denominator. So if we do the same system now, A, B, C, this multiplies, and that gives us the top line 3 times 3 3s of 9, so that's plus 9. And then this defines the numerator and denominator. And in fact, in this case, I've passed in sys1. I think it takes both. Some of the MATLAB commands take both. So then RL tool sys1, I've shows the axes here. Probably don't need that command. Then we get a new type of window comes up. Let's have a quick look at this. I quite like this. Do copy, go back into MATLAB, and we'll get rid of this. Just delete it, and then we paste our other code in. This is using RL tool now to do the job for us. So go on to editor and run, and there's the transfer function, just to check it's okay. And with a bit of luck, at some point in time, here it comes. It takes a few seconds to get RL tool going. It's quite a sophisticated little package, this one. This gives you an option. You can switch between this one and this one. So if this is your root loci, and this is your transient response you've got for the particular gains you've chosen here. So these are the gains we've chosen. So you can move these about now. So if you just grab hold of these, you can move them about using the hand. And you can see, I'm going to go for a damping of 0.6 if I can. So if I can do this the other way. What I'm doing is I'm going for this number down here. So I'm putting my mouse on top of here, moving that up and down to get a 0.6 there. So I don't know if I can do it. It's going to go down a bit. Maybe if I made it very big, it might be easier for me to do. Here we go. So if I move it down, the trouble is I can't see because of my try my best here. It's best I can do that. That's about 0.62. My mouse is just not good enough. If we then clicked on transient response, this is the transient response we get with that particular damping ratio. So that could be your performance you've got. If you didn't like that, you can say, oh well, I could do with a bit more overshoot, just push this point out a little bit more, and then you get a bit more overshoot. If you think it's not enough, it's too much overshoot, just drag it in a bit and then run it again. You'll get one without overshooting. So using this little tool now, we can get it to choose what controller gain would be suitable for me. It tells you in the window what the gain is somewhere. Let's go back to this one. So in this one, it tells you what the current gain. Let's tell you somewhere where the current gain is. So it tells you where the closed loop poles are, where the pole is, what damping ratio is, and what natural frequency is. I'm surprised it doesn't give you the gain, but it must do somewhere. But this is a nice little tool, and you can use it to move your root loci, move about your root loci, and look at the transient response at the same time. So it's quite an interesting little graph. Let me just make this bigger. Does it tell us what the gain is there? No, it doesn't. Oh well, if it tells us what the gain was, it'd be even better, wouldn't it? Maybe it does. I can't see it. So anyway, this is a little tool, which is quite amusing, isn't it? You can move this around here like this. We go up to say more over here somewhere, unstable, and we can then look at the step response, and there we've got unstable. Yeah. If we weren't too happy with that, we could bring it back stable. Just bring it back to here. It's just about stable now, and it's quite oscillatory. Then if we're not happy with that, just pull it in a little bit more. It's now got quite a bit better, so got a better response. So you can see you've got the flexibility here to assess the performance as you go along, which is quite a nice little feature. So as I say, in this one, you can move this around. You can then get your root loci plot in there, get your transient response as well from the same sort of system have a look, see if it's what you like. If it's what you like, then go for it. In the course, we'll have looked at the angle and magnitude criteria. So these are more advanced topics which tend to appear in the exam questions, but they essentially work out where you are on the root loci and where the root loci is. I don't want to spend too much time on it, but Matlab does those calculations for you. So when you move your mouse along, then the frequency and the damping and the roots are on the root loci are displayed for you. So it's essentially using the angle and magnitude criteria as you drag your mouse along here. That's how it's getting the values. But all you need to be able to do is just read the values off the graph, because it does it all for you, which is very pleasant in Matlab. So here's your knowledge check now. Here's a little control system. Have a go at building the control system in Simulink, then simulate it. Then plot the root loci of the open loop system. So this is the open loop system. So enter that function into Matlab and plot the root loci of that function. And then you'll be able to choose suitable values for gain in here. So try and find a value that gives you damping of 0.6. Try and find a value of gain that makes it go marginally stable. Try one that goes unstable as well. And then simulate the systems and compare all your values. And you could even use RL tool to do the same thing. And that will then give you good working knowledge of plotting root loci and doing all of the type of calculations associated with it. Right, so thanks for that. So this talk is on state space models, and we can represent a dynamical linear system by a set of state space equations. X dot is x plus bu, y equals cx plus du. In general, the du term is 0. Anytime you get a du term in, is if there's the same number of poles as zeros. But in all the examples we'll do, there'll be more poles than zeros. So D will be 0. So let's have a look at learning objectives. We want to understand the concepts of state space equations. Use Matlab commands to convert transfer functions into state space and go from state space back to transfer functions. We want to build a Simulink model of a state space, and in Simulink we want to simulate some state space control systems, and we want to compare your simulations with transfer functions. And finally, we want to look at simulating closed loop state space models as well. So there's a few things to do on understanding of state space representations and how they compare with transfer functions. So if we have a little idea here, here is an A matrix, here's a B, here's a C, and here's a D. And I could define the A matrix, the B, the C, and the D. Notice some semicolons in here to represent new lines. So it's 0, 1, new line, -5, -2, 0, new line, 3, C is on the straight line. So then we can type the command SS, and then round brackets A, B, C, D. We'll define sys then as some state space equations within Matlab. So that's one way of getting some state space equations into Matlab using the SS command, which must stand for state space. Now, there are various commands in Matlab which can convert from one thing to another. So a useful one is TF2SS. This is transfer function to SS, and you've got to pass the numerator and denominator of the transfer function to the function, and it gives you back a set of state space equations. You could also use just the command SS here, with that as the transfer function. So if you define this transfer function as sys1, you could have A, B, C, D equals, and then just SS, open round brackets, sys1, close brackets. That'd be another way of doing it. So the TF2SS works with numerator and denominator. The SS works with the name of the transfer function. You could also, the other one that we might want to do is to convert state space to transfer functions. So there's your state space equations. We want to convert to transfer functions. It doesn't do it directly into a transfer function. It does it into a numerator and denominator. So this structure is stored within square brackets, and you have to convert the numerator and denominator into a transfer function using the TF command. So they're the functions that we're going to be using, probably that function and that one there in the main to do our stuff. So these are our different ways of going around all the different things in transfer function, state space, pole zero models. The ones we're going to be looking at are these in here, really, these from state space backwards and forwards to transfer functions. So when we're doing this, as you say, we can represent a system using SS, A, B, C, D. If we do SS, where this is defined as a transfer function here, then we can get some state space equations, A, B, C, D. And if we've got sys TF, we could do TF sys SS as well to get at the transfer function. Let's have a look at some examples. Let's say now here's our little transfer function. 2s squared 8s plus 6 over s cubed 8s squared 16s plus 16. And so we could represent this now with this little bit of MATLAB code. But the numerator has 2, 8, 6. Denominator is 1, 8, 16, 6. So I've got numerator, denominator. Then I've put the system transfer function equals, and I get the TF, numerator, denominator, and I put system in state space. I've used underscore just to give these names here. It's equal to SSTF. So this is a case where we're using the SS command to convert a transfer function into some state space equations. So if we were to copy this bit of code, copy, and if we then go to MATLAB and put that code in here somewhere, and then run this, probably been better if I'd got that on a separate line, but you don't have to have it. But it's got the numerator, denominator. This sets it up as a transfer function, then the command SS will give us some state space equations. So if we run this, it then defines A, B, C, and D for us as the state space equations. So here we've got some state space equations, A, B, C, D, A, B, C, and D. So that's a quick way of getting from a transfer function to some state space equations. Now, so that's our state space equations. So this is another example of that. We've got a numerator and a denominator, and then this time we're going to use the command TF2SS. Now the advantage of this is we can define in here the exact names of the state space, and we might call them A1, B1, C1 and D1, for instance, to give them slightly different names. And it's using a TF2SS N1, D1, where this is the numerator and this is the denominator. So I'm just going to make these into a 1 for you to show you some advantage of using this function, because you can define explicitly here different names. You could call this Bill, Fred, Betty, Doreen or something, and they would be like the names of the different things rather than A, B, C, D. So if we take this bit of code here and copy that one and go into MATLAB, I'll get rid of this and just paste it in there, and then this one, now it gives me A1, B1, C1 and D1, so it gives me specific labels now that I can set up here. So this is a little bit better than the other function, I'd say, in the sense that you can label them with specific label names, which could be handy. One thing is if you've got some transfer function, remember, and you want to get the numerator and denominator, you can use TF data with name of the transfer function there, comma, and then in quotes V, another quotes. This command is handy for extracting numerator and denominators from transfer functions, because you might want to pass the numerator and denominator to some of these functions here. So that's worth remembering. If we want to go from state space to transfer functions, then we can use the SS2TF command. And this, you pass now the state space parameters A, B, C, D, or whatever they're called, through the SS to TF, but it gives you a numerator and denominator. It doesn't give you directly the transfer function. So then you'd have to convert then the numerator and denominator into a transfer function. So for instance, if that was the A, this was the B, this was the C, and that was the D, then we could say numden equals SS to TF ABCD, and then sys_TF equals TF numden. So this is going to, sys_TF now is going to end up as the transfer function here. So if we copy this little bit of code, this will convert some state space equations now. Don't want that one at the moment. Some state space equations, so I'll just get rid of this. Paste it in there. Even paste it in there. So this has got the state space equations, and this is going to convert it into a transfer function for us. So if we run this bit of code, there's bingo, back to our transfer function. Seems I've got a bit of a mark on my screen, but anyway, you won't see it. So that's an example now of going from some state space equations to a transfer function. You could name this whatever you wanted. You could just put your name in there. That would be straightforward. So next thing to look at is, once we've got some state space equations in Matlab, we might want to set up a little simulation in Simulink. Now these have got, there's a special box now in continuous models, which are the state space equations, and if we click on that box, we're going to get this thing coming up here. Now we could type in here the A, B, C and D as if we typed them in here, but it's quite a small area and it's easy to make a mistake. So a better tactic is to name your variables, your state space variables in Matlab with specific names, and then use those names here. So I've called this A, B, C and D, but I could have called this, like say, A7, B7, C7 and D7. This would be A7, B7, D, C7 and D7. And by doing this, it's quite a simple way of getting the data into Simulink, and it's easier to check when it's in an M file, to check that you've got it correctly, because you can easily miss out a semicolon or something, or put a semicolon in the wrong place, and it'll just say get lost, and it'll take you a long time to find it. So let's just have a quick look at that, shall we? We go back to here. If we go onto home and get Simulink going for a second, get a blank model here. So we could go on to get a library, and we're going to have a scope anyway, so I need a scope. Might as well so come into scope, and we'll need a source, a step. I can get a step out of this. There's a step, and then if we go on to continuous, we can then get some state space equations. There's two types of state space equations. This has got an E in front of it, this one hasn't, so the equations we're going to play with are going to be these type here, so I'll stick that one in there. And if we then join that up and join this up, then there's a little state space model now. Now if we double click on this, we can now type in there A, type in there B, type in there C, and sorry, I'm not doing this very well. Type in there D, then OK. And now we're about to run this as a set of state space equations. And here is the transient response. Now, if this is correct, I pull in a little transfer function here and connect that one up to there and give this two outputs. So go on to signals on ports, number of ports onto 2, and then connect this one onto there. If we run these two now, we'll notice now they're not the same. Well, that's pretty obvious, I suppose, because this transfer function is not coming from these state space equations. So if we go back now to our transfer function that we came from originally, it's this one here, which is s squared plus 8s plus 6 over s cubed plus 8s squared plus 16s plus 16. So we could take now these two polynomials and enter them now into our simulation. So we double click here. So what I want here is open brackets 1, 8, 6, and the bottom line was open brackets 1, 8, 16, 6. So I now type OK. So you can't see this, so I'm just going to move that back a bit that way, move that over there, and then I can just make my box a bit bigger. And there we go. So now this time, this is the transfer function. We converted this transfer function into these state space equations, and therefore we should get the same result to do. And we do more or less. Not perfect. Not far off. Should be perfect. I'm not sure why it's not perfect. But that's an example of the transfer function and the state space equations coming off. Let me just go back and have a look at that. Oh, I'd missed out a 2 here. Notice I missed out a 2 there. So that's where it wasn't quite perfect. So even I can make a little mistake. So if we go back to here and put the 2 in, hopefully they will match up. So if we run it again, oh, it didn't like it. Didn't do okay. When you've done, you have to do okay for it to put it in the box. Run it again, and this time spot on top of each other. This shows you a little trick really, that if you've done it one way and do it another way, unless they both are exactly the same, you've made a mistake. So I was able to use that as a little thing to realize I'd left that 2 out, which is easily done. But it allows you, when you see that both are sitting on top of each other, you know you've done it correctly. So there's an example now of a state space simulation, and here's an example of a transfer function running alongside it, and you've converted from there to there, or you can convert either way. That's going to be a possibility. So there's our state space, and we could do closed loop state space as well. So here's some closed loop state space equations, which we could set up. And again, if as long as we made sure that A, B, C, and D were inside there, these two systems would act in exactly the same way. So this is how you could remove that box, replace it with state space box. As long as the right state space equations in here, it will give you exactly the same results. Now, the last thing to look at is closed loop state space equations. This is where we use some feedback on the closed loop system. So we have U is some gain times the error, and then there should be a little dot in there. X dot is AX. This is the closed loop state space equations here, and we'll be covering this in the lectures. But I just wanted to sort of throw this one in. The interesting thing about this is that this matrix here now becomes the effective closed loop state space equation. So if we entered in the original A, B, C, and D that we had from the previous example, chose a gain of 2, I could work out the closed loop state space equation as A minus BKC. I could work out the new closed loop B, which is given by K times B. The C is the same and the D is the same. So this now gives me a format for closed loop state space equations. So let's just see what we mean by closed loop state space equations. Well, here's a little example. Here's our original system with a feedback gain of 2 around it. We've taken our state space equations from here and we've stuck them in there. Got the same 2, so this should be the same as this one really here. Now what I've done here is I've eliminated this loop here, or this loop, by forming the closed loop state space equations. So this is the trick, I suppose, the difference between open loop state space equations and closed loop state space equations. The nice thing about closed loop state space equations is this equation never changes. All that changes are the matrices. So this gives you a very quick way to compute a closed loop system if you wanted to. You can just compute A minus BKC, BK, and off you can go. So we've used these equations to put those in there. So that's where here I've got ACL, BCL, CCL, and DCL in here, and in here I've got the ABCD. And then when I run these, it should give me, I've done it correctly, all three should sit on the same graph. So I've cheated a little bit here. So here, this is my transfer function original system, gain of 2. Here's the state space equation. So if I click on this one, that's the ABCD. So that's the original ABCD. Here though, I've got ACL, BCL, CCL, and DCL. These are closed loop state space equations. So there's three formats of the same thing now: transfer functions, state space, but with the state space as a block, and these closed loop state space equations. And when we run this, have a look in here, and again we get this one transient response because they're all the same. If I was to change something like, say, change that to a 1, then what'll happen now is they'll be different, won't they? Because one of them changed. If I was to change, say, that one to a 4, again it'll be a bit different. So we got a whole family of them now. Probably that one is the one that's down from down there. So we can see, as long as you make them the same, that with a 2 in there and with a 2 in there, then when you run them, then you'll all get the same. In other words, this closed loop system is the same as that closed loop system, and this is a closed loop system, but now it's formulated as a single block. We could have used feedback as well here, couldn't we, to simulate this, replace this as a single block. Add a fourth one in here that did the closed loop simulation. So we just do that one. I'll just show you that one. It's a final little trick. So I've got 2, 8, 6, 1, 8, 16, 6. So we'll just quickly go into Matlab. Go here. Let's have a new start again, shall we? So let's put numerator equals open square brackets 286 and denominator equals 1, 8, 16, 6. Then I'll put sys1 equals tf numerator denominator. I'll put sys2 equals feedback. Remember our block diagram reduction techniques now, feedback, and the forward loop gain is 2, so it's going to be 2 times sys1 comma 1, because the feedback gain is 1. So because we've got a feedback gain of 2 in here, so we're going to use the gain of 2. So if we run this one, go on to editors, run this. Here's my closed loop system now, which is 4, 16, 12, 4, 16, 12, and 1, 12, 32, 18. So here's my closed loop system now. So if we put that transfer function in, we should get this closed loop transfer function should behave the same as all the others. So if we go in here now, and we'll just do a copy this, shall we? Copy and paste. And so we've got this in here, so we can just connect this now onto there. Now we haven't got enough outputs here, so we need 4. So I'm getting too quick with my fingers. Put some things, so go on to more, and we'll go for 4. So we can get 4 in there. So it's gone in the wrong place, but then I've just connected up a bit badly like that. There we go. Now, so these numbers are wrong now. We now need here, click on this. So the numbers should have been in the new one 4, 16, 12, and on the bottom line we should have had 1, 12, 32, 18. So this is our closed loop system now. So here's our open loop transfer function with a bit of feedback around it. We converted this into some state space equations, and put the same gain. So this is equivalent to this. We've done block diagram reduction really on the state space equations to get us a single state space model, which we did previously. And then this now is if we use block diagram reduction on this to get this. So this is the same as this, and this is the same as this. And if I'm very lucky now, they'll all look the same. So if we run the simulation and double click on this, and again, they're all looking the same, which indicates phew, that I got it right. So that gives you some idea now about state space equations and converting from state space equations into transfer functions and from transfer functions back into state space equations. State space equations are useful for more advanced flight control system design. In particular, things what are called Kalman filters, which is a very popular form of control system used in most aerospace applications. So, before I get carried away here, let's go to the next slide. I have a little knowledge check for you now. So here's a little feedback control system. So we need to build that control system in Simulink, then simulate it. Convert the transfer functions into state space equations, and then replace the transfer functions with state space equations and simulate it. Form the closed loop state space equations and simulate that as well. And if you like, you can form the closed loop transfer function and simulate that. So what I'd like you to do would be to do this example and eventually come up with 4 different answers like this and show that all 4 answers are the same. And if you can do that, you're very good. So good luck with that, and see you for the next lecture.